All right, one of the things that we weren't able to do when we did vectors in two-dimensional space was this calculation called a cross product. So we've done a dot product. We've even done scalar multiplication of vectors. So we've kind of looked at two different things that are multiplication related. This is now the third. It's referred to as a cross product. And as I say, this is something that we can only do in 3 dimensions. So when we did the dot product, we were able to learn about it in 2 dimensions in R2. R2, by the way, stands for real number, but you're allowed 2 of them. So for example, you're allowed a real number here, and then you're allowed a second real number. R3 would be you're allowed a real number, another real number, and another real number. So 3-dimensional space where real numbers are allowed to be selected. So the dot product we can do in 2 dimensions and 3 dimensions. Cross product we can only do in 3. Okay, it had no meaning in 2 dimensions. So we weren't even, it wasn't like we put this off. We couldn't do it until we talked about 3-dimensional vectors like we did the other day. The notation for the cross product is we're using an x, we're using the multiplication symbol. So we, as I say, we have a couple different multiplications. The dot product, we use the dot. The cross product, we use an x. And it's important, right? We refer to them as 2 different things. The symbol that we choose means the 2 different products. So we have to be careful. The dot product was a little bit easier to define than the cross product was. So here's how we go about trying to describe the cross product. It says let A and B be vectors in R3 arranged tail to tail, forming angle theta. And really that should probably say between 180 degrees. Remember, if we go over 180, we would just measure the angle on the other side instead. It says we define A cross B as follows. So we have a picture there. A cross B is a vector perpendicular to both A and B. So the new vector, this cross product, is a vector for one. That's different than the dot product, right? The dot product gave us a number. A cross B is a vector that's perpendicular to both A and B. So it has to be perpendicular to both vectors we started with. And its direction satisfies the right-hand rule. The way the right-hand rule works in this case, because I think there's rules like this in physics too. The way the right-hand rule works for a cross product, you point your fingers along vector A, along the first vector, so this is with your right hand, point your vectors along vector A, curl them through the angle, so curl them through theta, so that they point towards B, and whichever way your thumb points is the direction of the cross product. It's either going to be, when we look at it, we just see the picture like this, it's either going to be towards us or into the page. Those are the only 2 options when we draw it like this. In this case, point the fingers towards A, curl towards B. Your thumb should be pointing right back up at you. So for this picture here, the direction would be towards us. If I draw this, if I call that one vector A and that vector B, so the order is now a little bit different. In order to actually point your fingers along A and curl them through theta, the only way to do that is to point your thumb in. Your thumb has to go into the page. You should try that. You should actually make sure you're able to do that with your hand. It's a little bit awkward. It's actually lots of fun on the test because I get to watch you guys try and figure out how to curl your hands properly. This is only part of the definition, right? Where we've defined the direction. Because I said A cross B is a vector, so it needs 2 parts. It needs to be a vector, and so it has to have a direction. It also has to have a magnitude. This is how we define the magnitude. It says we still need to know the magnitude of A cross B. There's our notation. We've got the absolute value symbols. The magnitude of A cross B is equal to the area of the parallelogram created by A and B. So I've got vector A and vector B drawn there. The angles in between them because the vectors are aligned tail to tail. We're defining, and again, this is like the dot product, right? We're defining this to be the cross product. Someone said, hey, this is a good idea. So the definition is that the magnitude of the cross product is equal to the area of the parallelogram that would be created. And we need a way of actually calculating that, which isn't too bad. this is going back to grade 9 probably though, the way we calculate the area of parallelogram is we take the base and we multiply that by the height. So the base in this case, we could just think of as being vector A, right? Or in that case, the magnitude of vector A. The height is right there, right? The height has to be perpendicular. And it turns out the height's not hard to calculate using trigonometry because we'd have vector B there, and we said we knew what the angle would be between the two vectors. So the height is just the magnitude of B times sine theta. That means that overall, the magnitude of A cross B is the base, we said was the magnitude of vector A, times the height, magnitude of vector B, times sine of theta. And that should look pretty familiar, right? That's almost the same as the dot product. The dot product was magnitude of A, magnitude of B, cos theta. So very similar ideas here, but keep in mind the dot product was just that number only. It was just a scalar. For the cross product, this calculation, magnitude of A, magnitude of B, sine theta, is just the magnitude of the vector. It's a vector though, it has a direction too. So we're getting quite a bit more out of a cross product than we were out of a dot product. So let's try this one. This isn't a really hard calculation to do. It says determine the magnitude and direction of G cross H. So first thing I'm going to do, I'm going to calculate the magnitude of it. And really we're going to describe this then in two ways. The magnitude is the magnitude of G times the magnitude of H, and it's the cross product, so it's sine of the angle in between. So that's 8 times 5 times sine 30. Sine 30 is nice, that's just 0.5. So that's a total of 20. No units there, right? We'd never started with any units, but the magnitude of the cross product is 20. The direction has to follow the right-hand rule. So this, sorry, forgive me, this is, I can't show you, right? I can't put my hand up there. But what you're doing is you're using your right hand, point your fingers along G. So the fingers start at the corner, your hand goes here. Point your fingers towards G, and you need to curl them through that 30-degree angle to point towards vector H. And the only way to do that is if you have your thumb pointing into the board. So in this case, we just say the direction is, well, for me, it's into the board. For you, it's into your page or into the desk, something like that. Okay. This is all geometric, mind you. Right? We did all of this based on seeing the vectors and being told particular magnitudes and being told particular angles. That's all geometric. It's not Cartesian yet. Here's Cartesian. This is the formula for the cross product, and it's miserable looking. Right? It really is. You can see that there's some commas there. They're a little tricky to see. There's a comma, and there's a comma. It says if vector A is A1, A2, A3, and so on for B, then that's how you calculate the cross product in Cartesian form. Okay, it's that calculation. Good news, that isn't a formula you need to memorize. I'm going to show you another way that we can do it. But ugly, ugly looking formula. We are going to try it. I want to show you how it works, and then I'm going to show you another way that we can actually do the calculation. It's using the same formula, but sort of a shortcut to it instead. So we are going to try and calculate G cross H. So I'm going to write it all out. This is what it should look like. G cross H is, and I'm just basing this on the formula that we see above. It's G2 times H3 minus H2 G3. Right? That's our first component. And then the next one is G3 H1 minus H3 G1. And then finally we have G1 H2 minus h1 g2. That's the formula written for vectors g and h. The only thing maybe that to notice is a pattern. I mean, it's always subtraction. The numbers and letters are always flipped as you subtract them. And if you're calculating the first component, right, this component here, it doesn't have any ones in it. So, I mean, I guess if you're trying to memorize the formula, you could sort of base it on that. But as I say, we're not going to memorize this formula. From what we had above, let me see, I'm going to write this in. 4 was G1, it was G2, G3, H1, H2, and H3. So we're going to take a shot at making this calculation. This seems like something that I would screw up, so if I do, forgive me. I'm going to do my best. G2 is minus 1 times H3, which is 5. Take away H2, G3. Hopefully that's our first component. G3 is 0 times, 0 again, minus 5 times G1, 4, comma, G1 is 4. Sorry, now it probably just sounds to you like I'm mumbling. I'm just trying to keep this all straight. 0 times, okay, I think that's right. Again, if I messed it up, forgive me. Hopefully you guys got the right calculations. We'll actually go ahead and calculate this. That'll be a minus 5 take away 0. So minus 5. 0 take away 20 is minus 20. And 12. So that is the cross product in Cartesian form. Right, that's in Cartesian form. I'm going to try sliding all of this up for a minute. There's, again, that's how we calculate the cross product. Now, the verify here says verify that vector g actually was perpendicular to g cross h, because remember what we said was that when we find this cross product, the cross product is supposed to be perpendicular to both g and h. Right? That was what it was supposed to do. Now, if we want to verify that things are perpendicular, we do that by using the dot product, right? I can say if vector g really is perpendicular to g cross h, then g dot should equal 0. This is one of those points where I always think back to, remember what life was like in grade 9 and you guys were first starting high school and we started teaching you some algebra and we used variables and stuff. If we just wrote something like that down on the board, it's one of those ones where you'd have absolutely no idea what we were talking about, right? It looks completely foreign. And now you can look at it a couple years later and go, okay, that sort of makes sense. I hope. I hope. Let's try calculating this dot product. Vector g was 4 minus 1, 0. Cross that with our, dot product that with the new vector we found, our cross product, minus 5, minus 20, and 12. And if we do that, we get minus 20 plus 20 plus 0, which sure enough, we get 0. So our conclusion from that is that vector g really is perpendicular to the cross product. You could test it with vector h if you want to. You do the same thing. Actually, it's easy to do. If we do, what am I looking for? I'm looking at this guy, cross product with this guy, or dot product. 0 times minus 5, 0. 3 times minus 20 is minus 60, and 5 times 12 is positive 60. So we end up with 0 again. So it worked. G cross h, that's a good sign. That means I did my calculation right. That means G cross h really is perpendicular to both of the vectors that we started with. Okay. Now, as I said, I don't want you to have to memorize that formula, but we're going to be calculating cross products like crazy. So you're going to need to be able to do it. This is the method that seems to work relatively well, certainly better than than writing that formula down. There's some other similar tricks to this, but basically it's set up this way. And that's the best I could do as far as writing it down in words. Write the first vector, start with it. Anyway, let me just show you. Read that, but this is what it looks like. What you do is I'm going to take vector g, and I'm going to write vector g down, but I'm going to start at the second number. So I start with the -1, then the 0, then loop back 4, and then I write the -1 down again. Okay, so I've written vector g, starting at the second component and repeating the second component at the end. Do the same thing for h. So you go 3, then 5, then 0, and then 3 again. And to calculate the cross product, what we do is it says we take the down product minus the up product. So how do I want you to picture this? We're going to take a box around 4 of the numbers, and we're going to take the down product minus 1 times 5 and subtract the up product, which is 3 times 0. So -1 times 5 is -5. Take away 0, we get an answer of -5 there. Okay. Then we take our box and we shift it over to the next set of numbers, and we do the same thing. 0 times 0, take away 5 times 4. So 0 take away 20 is -20. And then the last one, slide the box over again, down product minus the up product. So 12 take away 0 again is 12. And let's back up for a second. I hope that's the same thing. -5, -20, and 12. So same answer. This slide used the formula. This slide used this slightly easier method. Okay, it's a nice way of being able to calculate the cross product, just writing some numbers down. Okay, well, as I say, we're going to be doing that a bunch, so we'll get used to that calculation. We'll do it again right here, in fact. Determine the area of the parallelogram shown. So this is, the title there says application. It's a perfect application of using the cross product. Determine the area of the parallelogram shown. You've got 4 points. And notice that they're points, right? They're not vectors. But something that we know is that the magnitude of the cross product, we were defining this, right? The magnitude of the cross product was equal to the area of the parallelogram. So this is the way that we can use the cross product for a geometry question, for an area question. What we need 2 vectors. So I think these are probably the easiest two. Vector AD and vector AB. Notice they're tail to tail, right? That was important. We need them to be tail to tail in order for this to work. So if I consider those two, vector AD, so going from A to D, to go from 1 to -2, I subtracted 3. 1 to 1, I did nothing. 3 up to 7, I added 4. So there's vector AD. And vector AB was 4, take away 1, 0. So I have vector AD and vector AB. What I need first is I need to actually calculate this cross product. So I need to know what AD cross AB is. So what is that actually equal to? Well, in this case, we're given these values in Cartesian form. So I'm going to use that trick that we just had. And usually what I do is I just write the numbers down off to the side somewhere. It's really important to write it down. This isn't not something you do in your head. So remember, start with the second component. So 0, 4, -3, and then repeat the 0. Second vector was -1, 0, 4, and then -1. And I'll put the box in there again. Hopefully that helps a little bit. In order to make this calculation, we were doing down products minus up products. So 0 times 0 is 0. It got to be a little careful here, right? 0 times 0 is 0. Take away the up product. The up product was minus 1 times 4, so minus 4. But I'm taking that away, right? 0 take away negative 4, which becomes a positive 4. Next one. This looks a little bit easier. 16, take away 0. It's just 16. 3, take away 0 is just 3. So the cross product itself is 4, 16, 3. And that even defines a direction, right? Keep in mind, and I should have mentioned it before, I've drawn that parallelogram flat, but I've given 3 coordinates. Right? Point B is 5, 0, 3. This is a parallelogram in 3-dimensional space. But there was no need for us to try and draw it or picture it in 3D space. Okay, it didn't matter. It's not making any difference that it's not drawn 3-dimensionally. Right? We're able to do all of the calculations we needed to simply by drawing it the way we have. Going back up to the top there in the green, it said the magnitude of the cross product is equal to the area of the parallelogram. So the area equals the magnitude of the vector 4, 16, 3. And to get the area of a vector, that was using our Pythagorean theorem. And what does that turn to be? I get 281, I think. Not sure if that reduces or not. Well, we'll leave it like that for now. Square root of 281 is the area of that parallelogram. And that's a, well, it's a pretty slick way of being able to calculate a parallelogram, the area of a parallelogram, especially one that's in 3 dimensions. Okay. Let me just move that on because I got to slide this note out. This is the last thing for us because this is going to come up. The question that we just did asked for the area of a parallelogram, and you'll see that sometimes. But another common question, honestly the one that I ask more often, I suppose, would be to find the area of a triangle. So if I'd asked you for the area of triangle ADB, that would be this triangle right here. Well, the way you calculate that is you get the area of the parallelogram, and then you just divide by 2. So if you see that, if you see a question where it's asking for the area of a parallelogram, you do it the same way, or excuse me, if it's asking for the area of a triangle, you do it this way. You find the cross product, you find the magnitude of the cross product, but then once you're done, you divide by 2. So in this case, the area of that blue triangle would be square root of 281 divided by 2, just be half of it. All right, so there's your cross product, and as I say, now we've covered most of the calculations that we've needed. We've done dot product, we've done cross product. Those are the big calculations that we need to be able to do to handle stuff in 3 dimensions. So we'll use them a little bit more. Most importantly now, as you go and try the homework, just getting used to trying to do those calculations and be really, really careful as you're doing the calculations, because it's just arithmetic. It's just addition and subtraction and multiplication. But if you start slipping numbers or getting minus signs in the wrong spot, you start to get wrong answers piling up real quick. So as you're doing the homework, just take care in practicing it and practice using this trick of writing down the vectors and doing the down products minus the up products.